Hello, everybody. It's time to begin. I would like to start by showing you some parts of the previous lectures. And to this end, I'm going to share the screen and show you the PDF file. Okay, it's open. It's right here. Can you see the PDF file? Please confirm.
Yes.
Okay, good. So we stopped last time at analyzing some propositions showing the factoriality of constructions we were enjoying recently. So one of them was a proposition about the factoriality of the EX construction, which Michał proved actually in the recitation class. And here I just would like to wind it up because it wasn't formulated properly a week ago. It was formulated properly by Michał during the recitation class, but not by me during the lecture. So I have to write it properly on screen. Okay, let me see. We are very close. It's very hard to find text in a very big file. We're almost there. Bayes' theorem. Yes, and you see, Michał, so I appreciate your help. So you can see that I credited this proposition to both of us. And what Michał did, which was a very, very nice observation, which is highlighted right here. Let me choose select, and I want to show. I don't know how to indicate. Oh, maybe with this, yes. Okay. So that's the part which I added. Actually, with Michał I did it. Now I typed it up. So the story is as follows: that if you take the category of pairs, where E is any graph and X is any subset of the set of regular vertices in this graph, then the assignment that constructs out of this pair the graph EX and a morphism F and an assignment assigns to a morphism from graph F from graph E to graph F. Morphisms Fx defines a covariant functor into the category of graphs and graph homomorphisms. So that's what Michał proved during the recitation class, and I just want you to see that it made its way to the lecture notes. Now, another thing which we were doing, and this is what Niklas started proving in the recitation class, was this lemma about factoriality of the extended graph construction. And here I deleted 2 items, so that's all right if Niklas will check them during the recitation class. I hope that he will. But I realized that they are not needed for my purposes, so I simply deleted them. Not because they're not true, they were true, but we will not need them. It turned out that we need more sophisticated assumptions to prove our proposition about the factoriality of a construction of a conpath algebra. So this we discussed. I'm going to skip it. Yeah, and this is here where we begin. But before I switch into the whiteboard, I would like to recall from, I think, the first semester, the concept of the partial order between paths. Okay, I have to explain this symbol of being less or equal to in the space of paths. And to this end, I have to go back quite a bit. Let me try to see if search works. Yes, find, and I'm looking for partial order. Next one. Wow, 7 matches. Next one. Yeah, okay. So this is a general definition, and this is an example that we want. Yeah, so this is precisely a formula that I was after. So imagine that we have any graph, and we consider the space of all finite paths in this graph. We say that one finite path is smaller or equal to the other finite path if and only if there exists another finite path gamma, such that beta can be written as the concatenation of alpha and gamma. All right? And here it's very important that for the path alpha to be smaller than path beta, it has to be a subpath of path beta, but in a very specific way. It must be the beginning of part beta. It cannot be the end, it cannot be the middle. The beginning of a subpath is here the same as the beginning of a path. And it simply means that the first, say, n edges of your path beta, which is bigger, must be exactly the edges of your path alpha. And I emphasize here the word first. All right. Okay, I think we are now ready to rock and roll on the whiteboard. So I stop, I kill the Adobe reader, and I stop sharing. And now I start sharing the whiteboard. And we start doing things that are new. I'm not making any technical experiments today, but I have another reason to ask your indulgence. Well, I spent the night, most of the night, proving a new result for you for today's lecture. So I'm a little bit of a zombie due to the sleep deprivation. So please forgive all my slips of tongues and other clumsiness. But here we go. I take my magic pen. I lighten up my screen. And well, we continue. But first, before we get to this result, which I just so joyfully announced, I mean, this is a very small and minor thing. I'm going to put it into my joint paper with Alexander Fry and Mariusz Tobolski. Nevertheless, at this level of generality, I think this is new. And I think this is important that we really understand what are the optimal, the minimal conditions for certain things to work. And when I say certain things, I mean this covariance of the constructions of different types of graph or path algebras. Okay, so I'm about to show you, but first, okay, first I want to make a number of small comments concerning these two things which we just finished, notably the proposition concerning the factoriality of the EX construction and the lemma concerning the factoriality of extended graph construction. So about the latter, you see, you might think that it's a good idea to combine them, right? I have the EX construction, I have the extended graph construction, so maybe somehow I can combine both of them and see if they commute, if they are compatible. Well, I want to convince you that this is not a good idea. So let me write it like this: combining lemma and proposition, and I know what I have in mind. I will not write the numbers, doesn't make sense on the whiteboard. Proposition is problematic because of the following effect. If I take the set of all regular vertices in a graph E, then in general, it's not the same as a set of regular vertices in the extended graph, E bar. And I emphasize in general. Because you can take some stupid graph with no edges and it will be equal. But if we are to study some factoriality, we must use a big quantifier, it must work in general. Okay, so indeed, let me argue about this. If V is a vertex emitting one edge, sorry, and receiving infinitely many edges, so that's the situation. I have my one vertex V, it emits one edge and receives, say, countably infinitely many edges from somewhere else, okay? Then, obviously, V is regular in E, but not in E bar. Because it is an infinite emitter. Okay, in the other direction. So, so I just proved that the inclusion one way doesn't work. The inclusion the other way also doesn't work. So let me now show you the following example. So also, if V is a sink, in E, receiving one edge, then we have it the other way around. V is not regular in E because it's a sink, but it is regular in E bar. And for instance, we can take our favorite Teplitz graph and look at this vertex V. Of course, in E, this is a sink, but when you look at E bar, well, it emits this edge E star, and it emits only one edge. So of course, it is a regular vertex. Okay, and therefore, this potential construction you might hope for doesn't work, right? So consequently, if you take some subset X in regular vertices of E, then the symbol E bar X need not make sense. It might, but it did not make sense because we might have that X is not contained in the regular vertices of E bar, right? And when I look at such an expression, well, for this to make sense, X must be a subset in the regular vertices of E bar, but it might not happen, all right? As I showed you very simple examples when it might fail. So the naive construction at which we start in the, say, left upper corner with a pair EX. And on one hand side, we assign to it, say, EX, right? This always works. And then we can bar it. So this combination, of course, always works. We can always have the X graph metamorphosis of E via X into EX, and then we can extend it. This always works. But if we proceed the other way around, and here I'm sorry, maybe there is some more natural way, but I don't quite see it. And we can do nothing to X when we do the extension because the set of vertices is untouched by the extension. So I don't see any natural construction, but maybe there is one, okay? But the only easy, obvious construction which comes to my mind is that I extend the graph itself, but I don't touch X. But then I'm bumped into this problem. So when I try to construct E bar X and happily write that they are the same, well, I'm running into the problem that E bar X doesn't make sense in general, okay? So if you have some better ideas, especially you, Michał, about this issue, just let me know. But the only escape is that we also have some X bar done, but I have no idea how to do it in some natural way, okay? And I'm not sure it's worth researching. I'm just alerting you to some subtlety. Okay, so this was my first comment, which is a direct follow-up of last week's, previous week's lecture. And another comment is about, well, actually it's not a comment, it's the introduction of a new class, of a new category. And this is the category which we're going to need. Not the category IIPG, which I introduced a week ago. This turns out to be useless, but a category which I call MIPG. And well, I can put it as a definition. And this is exactly what we will need in our proposition. So MIPG is the category of graphs so objects are all graphs, no restrictions, with morphisms being path homomorphisms of graphs injective when restricted to vertices, and satisfying a very peculiar condition which I'm going to write like this: f less or equal f e prime implies e equals e prime. Okay. And this is in the sense of a partial order which I defined for you just a moment ago. And they are satisfying whenever, when, or if you want, when restricted to edges. So see, my mistake was that I thought that the injectivity on edges is sufficient, and this is why I asked Niklas to prove a lemma about this IIPG category. But I'm going to show a counterexample. It's not sufficient. This is a stronger condition, which of course this implies injectivity on edges, because if f of e is equal to f to e prime, then of course f of e is less or equal than f of e prime, and if it implies e is equal to e prime, you've got injectivity on edges. But it's not sufficient. And here, let me make a small spoiler, that the reason is that not only you have to be injective on edges, but also the paths which you assign to different edges have to be different enough. So what is not different enough, if to one edge you assign path alpha, and to another edge you assign an extension of this path, that's not good. They are not different enough. Okay, then the functor is not well defined into the category of algebras. Okay, so that's this is why I had to write a stronger condition using this partial order. Okay, and well, then you can define this category MBPG as the intersection. Also let MBPG be just the intersection of MIPG and BPG. I just don't want to write it again, but MBPG is a category of graphs with morphism being path homomorphism of graphs, bijective on when restricted to vertices, and satisfying blah 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 on edges. And of course, when we go to BPG, remember this is no longer the category of all graphs. This is the category of all graphs with finitely many vertices. Okay, so that when we assign to them unital algebras, and our morphisms are unital algebra homomorphisms. And yeah, okay, so this was a definition, and now after I've done this definition, I can make one more comment. And this comment this time is about well, why does it fail the lemma? Why doesn't this construction of extended graph, an extended morphism of graphs, preserve this subcategory? Well, I will show you a specific counterexample later on that it doesn't. But let me here just announce it, that as a remark. the end of anchor sign E bar to E, F bar to F, does not restrict well, I can say it does not restrict because I'm talking the whole category. Sorry, forget the in general. Does not restrict to the subcategory. M, I, P, G. And of course, the same is true about VPG, but here the finiteness of the number of indices and the bijectivity between them is irrelevant because what it is about this fancy condition which I wrote over here. So please remember this condition. I call it the M condition instead of monotonicity condition. Oh, this is like anti-monotonous. And that's actually very important when you want to do path homomorphism of graphs, when you want to go beyond the usual tame category of graphs with graph homomorphisms. Okay, so I think we are now ready for the main dish of the day. This is what took most of my night to prove it. But although there's nothing complicated in the proof, there are no fireworks, no brilliant ideas. Very much like with this EX construction, the whole, if you want research input is to figure out what are the desired conditions. Once you figure out what they should be, proving that they are, it's really easy. Though not trivial and requiring some work. But first, I need to recall something. So KA is the category of algebras over a field K. And UKA with morphisms, algebra homomorphisms. So here's the category of unital algebras. With morphisms being unital algebra homos. Okay, we're ready to rock and roll. I call it only a proposition because I try to have the following heuristic structure that when I'm proving something for con path algebras, this is a proposition. And when I prove something for relative con path algebras, general case, this is a theorem. And then when I go to Levitt, which is a special case of a relative con path algebras, this is a corollary. Okay, so this is sort of the hierarchy of concepts. First, we prove something much easier, that is with con path algebras, and it can serve then actually as a lemma to prove a general case. So it's not a waste of time to do it. And then as a special case of particular interest, that's what we want to do, we look at Levitt path algebras as a corollary. Okay, so even though it's the proof is like page long in my lecture notes, I call it only a proposition. And please forgive my handwriting because I already got used to using much better equipment than my laptop at home. I mean, this is a great laptop, but writing on the screen of a laptop is by far more difficult than writing on a professional graphic tablet or the super duper digital whiteboard that we have at IMPAN. So I hope you can read my handwriting. I'm doing my best, but it's not so easy because I already forgot how to write on the screen of a laptop. It's easy, much easier to get used to something better than to something worse. Okay, so we have a certain assignment and we claim that this is a function. So assignment. Which is what? I take my category of MIPG. So here I have all graphs, okay? So here's any graph. I find to it the concav algebra over a field K. It's not necessarily unitary, but it is an algebra over a field K, all right? So this is what happens, object. And next, I'm taking a morphism of graphs. So here it's really important that I write this MIPG. Here it makes a difference. And I just define it for you. And to such an F, which goes from E to F, I assign an algebra homomorphism, which I will denote as F star C. C is, of course, for con. And of course, it goes from CKE to CKF. And I claim that this is a morphism in the category of algebras over the field K. And I have to define it for you. And it's defined in the following way, that for any path P in the extended graph of E, so FPE bar, okay? When I take an element in this concav algebra, CKE, which I denote as a class of chi-P, you know that every element is a finite linear combination of such elements. Then I assign to it, so this is what my algebra homomorphism to be does, the class of chi of F bar applied to P. Okay, so I hope it's clear what I'm doing. Here it's the class in the concav algebra of E, and here's the class of the concav algebra of F. And what I'm doing, I'm lifting the representative from its class I'm lifting the class to its representative. So I'm going from the class of chi-P to chi-P itself. And then I apply this functor of which, no, you don't know it yet, but it works on algebras. Okay, so in fact, at this moment, just a recipe. This is the whole point to prove that this is well defined. And the proof would have been much, much longer if it weren't for the fact that we can bank already on some things proven for path algebras themselves. And you will see that the usefulness of this lemma about the functoriality of extended graph construction. Anyway, right now, for just a recipe, you see what I'm doing. If I have any path in the extended graph, I can apply the map F bar, which I construct out of F, the extended path homomorphism of graphs. Okay, so it gives me another path, this time in F bar, so in the extended graph of F. All right, if I take chi of this, I have an element in the path algebra of F bar. I take the equivalence class and I'm in the con path algebra of F. Okay, so this belongs to CKF. Okay, and I claim that this defines a covariant functor. Well, Now, how about the case of unital algebras or graphs with finitely many vertices? Of course, it works as well, but I have to write it down. So furthermore, the same assignment restricted to MBPG so that's the category given by graphs finitely many vertices, and with extra condition for the edges, okay, and bijective on vertices, defines a covariant functor UKA to the subcategory of KA consisting of unital algebras over field K and the unital homomorphisms of algebras. Okay, so I think we spent the rest of today's lecture, well, I still have examples, but most of the rest of today's lecture proving this proposition. Okay, I think that the first part of the proof uses heavily a lemma proven in the previous semester, and I think it's important that I show this lemma to you. So this proposition 226. So let me stop sharing. I can always come back to sharing my whiteboard. Nothing will disappear. Okay, and I will now start sharing the PDF file. Okay, now let us try to find 226. So Control F, 226. Oops, no. Yeah. Okay. Here we go. So this is very important that you bear it in mind. Here it works for the ambient category IPG, so we don't have this extra strange M condition for the behavior of F on the edges, right? But you see, this assignment is basically the same. Especially if you look here, chi P is mapped into chi of F of P, chi of P. All right. So this is this F star, and this defines a functor as we want it. It's a functor into the category of algebras over K, and when we restrict to BPG, I have a functor into the category of unital algebras over field K. So that's the proposition, which, as you can see, it took how long? I mean, this is about half a page to prove it, all right? I mean, you have to make one computation to make sure it works. And it does, okay? So this is this one thing we're going to use, and of course, the lemma. So now let me flash the lemma one more time, because we saw it already at the very beginning. That's the proposition. Yeah, here's the lemma, right? Oh, come on, why do I want to highlight it? Yes. Well, actually, I should highlight all of it. Okay. So that's the lemma. That's the lemma, which defines this extended graph construction and extended morphism construction. And it has this beautiful property that the categories of interest, which is IPG and BPG, are preserved. So in other words, if I do the following thing, I start in my category of graphs, in my IPG category, okay? So morphisms are IPG. And then I apply first, I go from E to E bar. So first I apply this functor, the bar functor. But the bar functor is an endofactor on IPG. It preserves this condition, okay? So if if f is injective on vertices, then so is f bar. So we have an endofunctor, okay? And the same holds for VPG. And Niklas will show it to us today, okay? So first I apply this bar functor, and I know it's a covariant functor. This is the lemma which was proven, well, will be proven in the recitation class today by Niklas. I mean, it was partially proven today. We'll have the rest of the proof. And then I apply this path algebraic functor, which I know again is a covariant functor. The composition of covariant functors is a covariant functor, okay? So when I apply now this path algebra functor, well, then I'm going from E to path algebras to the path algebra of E bar. So this is the composition of two covariant functors. And it works because I can combine this lemma 241 and proposition 226. Okay. So now I can stop sharing and start sharing again. Whiteboard share. Okay. So combining position 226, which you just saw, and lemma 241, which you just saw, with the fact that MIPG is a subcategory in IPG, we conclude that the assignment move a zoom bar. Okay. The assignment which starts from the category of MIPG. So here I take my graph E, and as I told you, assigned to this the path algebra of E bar. Okay, so of course it's an algebra over the field K. And now I take a morphism. So this is some map F E to F. And I assign to it the map from one path algebra, the path algebra of E bar, to the path algebra of F bar, and I call this F bar star. Okay, and now it's a morphism of algebras over K. And of course, well, the recipe for this F bar star is just as you can expect. But if I take any finite path in the extended graph of E, then typical element, or if you want the basis element of Ke bar, is exactly chi p. So if I define it as chi p, I define it everywhere. So by definition, what I assign here is F bar star. As you can guess, this is chi of F bar of P. And of course, now it's an element of Kf. Okay. So here, for instance, you don't have any problems with seeing that it is well defined because it's already linear maps, because all these chi p's give you the basis of Ke bar. And on a basis, you can do whatever you want, and it will be well defined. So here we don't have an issue like later on with the path algebra. We have to really prove it is well defined. And then we'll have automatically that is an algebra automorphism. Here, the only thing that we have to check is basically functoriality, but this is what was done. I mean, yeah, okay, well, I didn't say it quite correctly. This proposition 226 is not so completely trivial. Of course, you have a well-defined map of vector spaces, but you have to see that this is an algebra homomorphism. Okay, so it is a well-defined linear map, but is it an algebra homomorphism? Is it functorial? Yes, it is. This is what we obtain by the combination of the proposition and the lemma from the past. And now, why do I care about this MIPG being a subcategory of IPG? Well, this is obvious, because I take my element in MIPG. It is an element in IPG. Now I apply the endofunctor of this bar construction. So I land again in the category of IPG. And to the category of IPG, I can apply the functor of the path algebra construction. Okay. So this is why I can do this composition. First, I bar my F, and then I star my F. Okay. And I can do it because I'm working restricted category. So I thought erroneously that I must have that this bar construction it restricts to an endofunctor on the category of MIPG. No, it doesn't, but we actually don't need it. We actually don't need it because luckily it restricts to an endofunctor on the ambient category IPG. And this suffices for our purposes, okay? Because I repeat, I start in MIPG. It means I am in IPG. I apply the bar endofunctor, so I'm again in IPG. And then I apply the path algebra construction functor, covariant functor, because I have two. I have also a contravariant one. And I end up in the category of algebras of a field K. All right. So that's the story. But let me finish the sentence. Defines a covariant functor. And now we have to prove that it descends to a functor for conpath algebras. Okay. So in order to do so, we have to prove that the relations that by which we quotient our path algebra to obtain the conpath algebra are preserved by this F bar star. Okay. So now let us check that for any graph E, so no assumption whatsoever, any edge E in E1 such that F of E is of positive length, and this is just a bookkeeping assumption so that I can write that F of E is a path consisting of edges. Okay, and these edges I call F1 ... up to N, and N is at least 1. Okay, so this I need this presentation to do calculations, right? So for any edge in any graph, we have the following. I'm now under the technical assumption that F of E is of positive length. It need not be the case, but when the calculations are trivial and have to be written differently. So now our first main calculation. So I'm taking the equivalence class defining the conpath algebra, and this is the conpath algebra of F. All right. So what is it that I want to verify? I'm taking chi E star, chi E. And of course, when I quotient it to the conpath algebra on the E side, I'm just getting the class of chi of the end of E, all right? So I have to compute what this functor f bar star does to this element. So that's the computation in the path algebra of f bar, okay? Because I'm taking an element in the path algebra of E bar, I apply f bar star, and this gives an element in the path algebra of f bar. Okay, and we compute. So of course, first by definition of f bar. So first, what's the definition? How to use the definition of f bar star? First, I have to write this multiplication in a different way. So chi e star is just chi e is the same as chi e star e. Of course, these two edges compose to a path. So then I have chi e star e, and then I apply f bar to e star e. So I end up with a class of chi of f bar applied to e star e. But of course, by the definition of f bar, I just get chi. Well, so first, I know that f bar of e star e is nothing but f of e star fe, and then I can write separately chi's and separate equivalence classes. So let me not write everything. I'll just write chi f of e star times chi f of e, of course, equivalence classes, right? Because by definition of a multiplication or in the confab algebra, I'll multiply the equivalence classes by multiplying the representatives. Now in the path algebra, chi fe star and chi fe multiply to chi fe star fe, but fe star fe is precisely this fact, okay? So here we are. And now I'm using this notation. I know what fe is, all right? So now I can write it in the following way. I have first the sequence of classes starting from chi fn star, then chi fn minus 1 star, and so on and so forth, until I arrive at chi f1 star. So that's the first part. And now I'm writing the second part, which is chi of f1, chi f1, dot, chi fn. But remember, we are in the conpath algebra, and of course, when we have such multiplication of chi f1 star with chi f1 in the conpath algebra, they multiply to the class of chi of the end of f1. Okay, so I can now write it down as chi of fn star dot chi of f2 star. And now here I write chi of the end, and this is in f, right? So tf of f1, and then I write chi of f2 dot chi of fn. Okay, so this is just by our first Kunstfigure relation in the conpath algebra of f, all right? But then remember, this f1, comma f2 dot 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 fn is a path. So the end of f1 is the beginning of f2, and this means that this chi tf of f1 is absorbed into chi of f2. So I can just forget it. Okay, and now I can proceed by induction. So at the end of the day, of course, I will get just the class of the chi of the end of fn. Okay, but now it's not hard to see that it's exactly the same as the class of f bar star applied to chi te, this time, of e. Right? because what happens here, this F bar star applied to chi TE of E, well, it will be chi F applied to TE of E. Remember, it's just a vertex, so I don't have to write F bar. This is just F, but FTE is the same as the F composed with F. Okay, so I have the F TF of FE, right? But TF of FE is the same as TF of Fn because this is the last edge. And this is exactly what we have on the left-hand side. So this equality holds, and this means that the Kunz-Krieger relation, saying, roughly speaking, without all the decoration, E star E is equal to the end of E, that equality, this relation is preserved, okay? Now we have to prove that if I have two edges that are different, then say E prime is different from E, then chi E star chi E prime must be zero. And this is here where we need something more fancy. Okay, so this was just a simple calculation by induction, and now I know that sort of the first part of the first Kunz-Krieger relation is preserved by my construction. Now I have to prove the second one. Okay. But before I do that, I have to write one more thing. So note that if FE is the above calculation is trivial. It holds for trivial purpose. Well, indeed, let's look back. So assume that E is a vertex. Then E star is equal to E. We have chi E, which is simply chi E. Now when I apply it, okay, here I have chi of F of E, but chi of F of E is the same as chi of the end. Okay, so that's I cannot write this Fn. This whole part doesn't make sense. But already here I'll simply have chi of Fe, and if it is a vertex, instead of chi of Fe, I can write chi of the end of Fe. Now I commute F and the end, so I have F of the end of chi of sorry, it's better to write it down. I have, if E is a vertex, then my calculation F bar E bar E, this is simply F of E, okay? And well, actually, this is visible here, right? And now this is the same as the end of F of E. This is the same as F. I wrote at the beginning, I wanted the end. TF of F of E, but it's the same as F of TE of E. Okay. And that's exactly what we want. At the end of the day, I have the TE, I have TE of E, right? And I don't have to do all this induction process in between. So the calculation is trivial, and I don't want to write it again. Sorry, I scribbled like this at the corner. Maybe I shouldn't. I should write it more clearly. Here, I'll put colon here. And it all works so nicely because F bar E star E, when I repeat, when F of E is a vertex, Okay, then this is just f of e. This is TF of f of e, because the end of the vertex is vertex itself. Then this is the same as f of the end of e. And that's what we want. That's what we want, because now this is nothing else but f bar applied to the end of e. Okay, and the formula holds. Then I write the star, I write the chi, and I'm home and dry. Okay. So now we have to look at this more interesting case when I take two different edges. All right. By the way, any questions thus far? Okay, so I start the next step. So assume now that I have two edges, two different edges. So E prime, they are edges in E. They are different, and they have the same beginning. So that's our situation. I have a vertex, it emits E, and it emits E bar, E prime. And you might wonder why on earth I have such an additional strange assumption. Well, that's because if you really want to write the proof formally and precisely, rigorously, you need to use it at a certain moment. And when this doesn't hold, things are true for trivial reasons. So much as before, when I assumed that f of e is of positive length, I didn't do much, because when f of e is a vertex, my calculations are trivially true. It's just I have to write them down in a different way. It's much in the same way here. Simply when e prime and e start at a different vertex, then you have zero already when you look at e star times e prime. Simply the end of e star is not the beginning of e prime. So they already in the path algebra, they multiply to zero, okay? So I get the zero much faster than otherwise. But when they start from the same vertex, well, then I'm sorry, when I write e star e, it makes perfect sense, because the end of e star is exactly the beginning of e, okay? So this composes into a path. It is not zero in our path algebra or the extended graph. It vanishes later on precisely because of the con relations. Sorry, Kuhn-Krieger relations are the first type that define the con path algebra. Okay. So now under these assumptions, we are going to prove that we get a zero as needed. So under these assumptions, let me write by the condition and let me spell it out, because that's important that you have it in front of the eyes, that f e less or equal to f of e prime implies e equals to e prime for edges, of course. Well, we know that I have fe not less or equal to f prime, but also fe prime is not a subpath of fe, right? Because this is a symmetric condition. when I negate it, I have E not equal to E prime implies that this one inequality is violated. But of course, I can now write also E prime equal to E, right? So this is in fact a symmetric condition. You can exchange E and E prime, all right? If E is not equal to E prime, but also E prime is not equal to E. And then this means that both of these inequalities must fail, all right? Hence, and here I'm going to use this, first I'm going to argue that none of these can be a vertex. So hence, neither E nor F E prime can be a vertex. Why? Well, indeed, suppose that Fe is a vertex. Then Fe is its beginning, but now this is the same as F applies to the beginning of E. And now I'm using this assumption that the beginning of E is the same as the beginning of E prime. So I write it as F of SE of E prime. So you see, I'm using this assumption. And now I'm commuting the source map with my F map to write down as F of F of E prime. And you see what we established is that Fe is the beginning of F of E prime, okay? So I can write down Fe prime as Fe concatenated with Fe prime, because I just established that Fe is the starting vertex of Fe prime by this calculation. But this contradicts the inequality. I mean, it gives an inequality which is supposed not to hold. So contradicting and here we will have that Fe is less than equal than Fe prime. So contradicting our conclusion that Fe is not a subpath of Fe prime. Okay, and of course the reasoning for Fe prime is symmetric. So let me write down that Fe prime cannot be a vertex by the symmetric argument. Okay, but now when Fe and Fe prime have a positive length, I can write them down as a sequence of edges. So, okay, so consequently, both E and Fe prime are of positive length. I can write them as so FE, let me write down the path of F, so F1 dot Fn, and FE prime, I'll write as the path of primed F, so F1 prime dot, and this is F prime, N prime. I mean, there's no reason for N and N prime to be equal, okay? So now, the condition that neither FE is a subpath of FE prime, nor FE prime is a subpath of FE. I need both of them. Implies that there exists an index I, which is less or equal to the minimum of these two numbers, n and prime. Okay, such that Fi is different than Fi prime. Sorry, than F prime I. Okay. Well, indeed, imagine that this is not the case. So let's negate this implication, right? So what are we saying is that for every index which is less or equal than the minimum of n and prime, I have Fi equal to Fi prime. Well, but if this is true for every index, I look at these two numbers n and prime, and I take one which is smaller, or at least not bigger, they might be equal, okay? So without the loss of generality, let us assume that n is less or equal than n prime, okay? And then I take I to run from 1 to n, okay? And of course, it will satisfy this inequality. It will be always less than equal than minimum n and prime, if n is less or equal than prime, okay? But then this describes my whole path Fe, and this condition Fi equal to F prime I means that Fe is a subpath of Fe prime. And if it happens the other way around, that n prime is less or equal than n, then I use the symmetric argument. Okay. I hope the logic is clear, but this is very important. This is very important that now first I prove that these guys cannot be vertices. Then I write them as paths which are concatenation of edges. Well, that is at least one edge. And then this condition which we get from this special condition, this M condition in our category, this allows us to conclude that we have such an index I, that Fi is different than F prime I. And now we can use it in the calculations. Any questions here? Okay, so now it follows that that's my second main calculation. Well, I take, as before, I take my F bar star map, I apply it to an element in the path algebra of E bar. I write it as chi E star chi E prime. And you see, because I know that the beginning of E prime, in the path algebra, this is not 0. But when I go into the equivalence class defining the conpath algebra of F, then this should vanish. This is what I'm going to compute for you now. Okay, so let's do it. So of course, by the definition of f bar star. This is equal to the class of chi of f bar applied to E star E prime. Okay, but then of course I write it as multiplication. So this is very much as before when I had E prime equal to E. This is chi f E star times chi f E prime. Okay, you see this is here where I made my mental mistake. I thought, all right, if I'm injective on edges, then of course f E prime is different than f E, so it is 0. No, wrong. This is not true that if two paths are different, then in the concave algebra, the star of the first path times the other path is 0. That's not true. You must have a stronger condition that none of the paths is a subpath of the other path. They must be different enough. So this is if you want boosted injectivity. Okay. I need my M condition. Injectivity on edges is not sufficient. Okay, but I have it. I know now what is FE. I know what is FE prime, so I can write it out explicitly. Okay. So I write it down as chi Fn star dot chi F1 star. And here I start with chi F prime 1 dot chi F prime N prime. All right. Now this might be unbalanced. I remember I never told you that N must be equal to N prime. No, they are in general different. But now what happens? Look, if F1 prime happens to be, but now these guys are edges. This is what is important. So now if F1 prime is different than F1, then of course this multiplies to 0 because they're not paths, these are edges. Okay. Well, so if they are different, they multiply to 0 and we are done because I want to prove that this is equal to 0. But if they are the same, well, then I have a consquare relation. All of this will become, so let me write it down. So this will be chi F. Well, that's actually as before, so maybe it's useless to write it down, but I always started. So I will have this F, chi F2 star. And here I'll have I of TF of F1 prime. If they happen to be equal, then I start with chi F prime 2, and I finish with chi F prime N prime. Okay, so you see, if these guys happen to be different, I always hit a 0, which is what I want. But if they happen to be the same, well, I keep on shrinking this expression because again, this chi TF of F1 prime will be absorbed into chi F prime 2, so I can forget writing it. So my expression is getting shorter and shorter. And I inductively repeat the same steps at which I either hit 0, which I want, or I just shorten my sequence. But I'm going step by step. And at a certain moment, before I reach N or N prime, remember, I is always less or equal than the minimum of N and prime. So I will never run out of these objects that I multiply. But at a certain moment in my progress, I will reach I. And when I reach I, aha, I know that Fi and F prime I are different. So they do multiply to 0 by the consquare relation in the concave algebra of F. Okay, so I have what I wanted. I have a 0. Okay, so this shows that the full consquare relation. Okay, sorry. Again, to complete the picture, I have to discuss the trivial case in which the beginning of E is not the beginning of E prime. But maybe first, let me ask you, have you got any questions so far? So this was, if you want, at least in my opinion, the most interesting part. of the whole proof and the whole story. This is where the whole novelty lies. That's what people overlooked so far as I'm aware. Because nobody, okay, so first, basically nobody studies path homomorphisms of graphs. This was our innovation done a couple of years ago with Alex Kirvasitu and Mariusz Tobolski. But now when I looked into a published paper, I realized that we were not general enough, that we assumed something stronger than we needed. And today I got away with it, and I'm proving it to you under a weaker assumption. It's always great. You have the same product for smaller money. It's like Black Friday sale, you know. You pay maybe not half, but seriously reduced price for the same outcome, which is great. That's what we want in mathematics. Minimal assumptions, maximal claims. And here the whole point is that I only need to have this M condition on edges, and I don't need it on all paths. And when I have it on all paths, of course, things work because it's a stronger condition, but it's actually too strong. I'm going to show you too strong in the sense that it gives examples at which my functor exists. I mean, in which it works, the construction works. So that's why I'm asking you one more time. Have you got any questions concerning this point? Because it is precisely here where we use this M condition, which I invented this night, and that's the novelty, or discovered. I prefer to say discovered. Okay, there are no questions. I continue. I have to write this disclaimer. I mean, it's not a disclaimer, it's remark, observation. Note that if SE of E is different than SE of E prime, which of course might easily happen, the above calculation or the preceding calculation is true. Well, why? Let's have a look. That's the calculation we are doing. And I guess it's already here. You see, here we have a zero. This is already zero. Chi E prime, chi E star E prime, that already multiplies to zero. So I get my zero much faster. I don't have to worry about anything. Okay. So summarizing, we infer that F star C is a well-defined algebra homomorphism. Right, because you see what happens here. I have I have first my morphism of graphs. I go from F E. Okay. Now I go to the path algebra K E bar and KF bar. Okay, so here is my functor. And now I go to the quotient. So CKE and CKF. That's the quotient map. I'm dividing by an ideal. And here I have my F bar star. And here's my F C star. Okay. So I know from my previous proofs that this is a homomorphism of algebras and the square commutes, it's factorial. And now I'm wondering, well, whether FC star is well defined. Yes, it is, because it's induced. Why? Because I show what I just showed to you is that the ideal by which I quotient is preserved by F bar star. So F bar star maps the ideal on the left hand side to the ideal into the ideal on the right hand side. So the induced map exists and the square commutes. Okay. So basically what I did verify was that if I take F bar star of chi E star chi E prime, I proved that this is the same as F star bar of Kroneker's delta between E and E prime chi the end of chi E. This is in yes, in E. Okay. This is well defined because we verified this. Okay. And how did we do it? Well, we considered two cases. Well, actually three cases. First, when E prime is equal to E, and then we just computed what it was, and we got the result that F bar star applied to chi star chi E was just the same as F bar star applied to chi TE of E. Well, in a way, well, you can say that we did it up to. Remember, I did this calculation using these equivalence classes. Okay, around it, but that's sufficient. This is exactly what we want. If you want to put it formally, I take my element which generates an ideal is chi E star chi E prime less delta E prime chi chi TE of E. So this is an element. My ideal is the ideal generated by such elements. So what I really have to prove is that when I apply F bar to it, okay, I land in the ideal on the right hand side. But what is a better way to prove that I land in this idea if not by showing that the equivalence class given by dividing by this ideal is 0? Okay, so that's the same thing. I just want to make sure that the logic is correct, and it seems to be. Okay, so now it remains to check factoriality, but it's trivial. This is really obvious. So let me just write it down, that the factoriality goes with G, and now I put C and star, but this is the same as F star C composed with F star G star C. It follows immediately from the factoriality which we already established. If I take F circle G, so F composition G, then I bar it and star it, then I know already that this is the same as F bar star composed with G bar star. Okay. This is just a completely trivial calculation that one follows from the other. Okay, so we are done. We are done in this. non-unital case, and yeah, I wanted to finish right now as I announced, but as usual, I really don't know how to plan the time. No matter how hard I try, I always miscalculate the time I need to explain something. And I think that it would be stupid to postpone the end of the proof till the next time, especially that now what is left is really the easy part. Okay, so let me extend by these few minutes, and I will give it back to you. All right, now what I claim is that matching the same way makes sense to repeat the whole argument over and over again. Actually the same way. Again, combining the same proposition and the same lemma. So proposition 226 and lemma 241. And now this time with the fact that MBPG is a subcategory of BPG. So remember, in proposition 226, there is a part which concerns BPG instead of IPG and going into UKA instead of KA, so unital algebras over a fixed field K. And so you have this B part of proposition 226, and you also have B part of lemma 241, because Niklas will also show us today that this endo factor restricts not only to IPG, but also to BPG, okay? So now when we combine this all together, exactly as before, right? We conclude that the assignment now I take a graph with finitely many vertices, so MBPG. Assigned to its path algebra extended graph, and now this is a unital algebra. So this is an element in the class of objects of UKA. I apologize for my handwriting, but it's really hard to write when I cannot touch the screen. You see, the big advantage of this professional graphic tablet at IMPAN is that I can put my hand on it, just as I put my hand on the piece of paper. If I do the same here, just by touching the screen with my fingers, I make a mark. Okay. So I take a morphism. This is done exactly as before. No changes here, just properties are different, okay? Now this is a unital homomorphism. And of course, it's given by the same formula. Let this keep writing. So this defines a covariant function. So finally, by the preceding arguments, because nothing changes here, F star C is a well and functorially defined homomorphism of unital algebra. Is a well and functorially defined homomorphism of unital algebras. Unital homomorphism of unital algebras. Well, mind you, when we prove something for a bigger class, of course, it holds for a smaller class. So I know that this F star C is well and functorially defined for MIPG. So of course, when I restrict my graphs to graphs which have finite many vertices, and I restrict my morphisms to morphisms that are bijective on when restricted to vertices, nothing changes. They are still part of this ambient structure. So this means that this property of being well and functorially defined homomorphism of algebras is done. So the only thing we have to check the unitality, but it's a triviality because we observe that when I compute F star C of 1 in the algebra, 1 in the algebra is of course the class of 1 in my path algebra. But now I look at this definition of F star C. So this is the class of F star bar of 1. Okay. But I already know that from what I wrote above, that this is a unital algebra homomorphism. So this is the class of 1. Okay, so this proves the unitality. That's the only, I mean, this is a trivial argument that if you have a unital homomorphism, unital algebras, and you induce a map on the quotient algebras, then of course it remains unital by this trivial calculation. So that's the only thing you have to add to this claim that this assignment defines a covariant functor. And it does because of another application of proposition whatever and lemma whatever, and the fact that MBPG is a subcategory of BPG. Okay, I think it ends the proof, and this is a good time to stop and resume later on, of course, but let me just say that I'm very happy we managed to finish the proof. And well, as minor and modest as it is a new result obtained this night. And I'm happy with it because I really want to unravel what the minimum conditions are, really the optimal conditions for me to have a covariant functor from the category of graphs appropriately fine-tuned to the category of algebras, and this functor is the construction at this time of conpav algebras, but later on it will be relative conpav algebras and Leavitt path algebras. I want to see which assumption is responsible for which modification. So for me, a good reason to start with conpav algebras, not Leavitt or relative conpav algebras, is that I see what is the effect of imposing just one Kunst-Krieger relation. So you see, when all I wanted was just to have a path algebra, the only restriction I had to put on my path homomorphism of graphs was injectivity on vertices. That was necessary. Otherwise, this would not be a well-defined map between path algebras. But now we had to add this strange end condition. And in a week, I'm going to convince you that I really did some fine-tuning, that assumption which I had in the published paper was too strong, and the assumption that I hoped for a week ago was too weak. So this is like the perfect thing in between. And that's the cherry on the cake, which I want you to take home and remember, this end condition, which allows us to prove this factoriality, and it doesn't kill interesting example, and works. Okay, so let's make now a half-an-hour break and resume 4:20. Let's resume at 16:20, 20 minutes past 4. And then we do the recitation class, and Niklas will continue. I stop recording, see you in half an hour.